Hello everyone and welcome to our session on dynamic system modeling. I'm Nilo Hassan and today we will discover one of the most powerful mathematical tools for understanding change in the real world, differential equations. By the end of this session, you will be able to first explain what differential equation is and why it's important, classify differential equation into first order and second order types, solve simple examples of first order and second order. Third, solve some simple examples of both types. And finally, connect the solution to the real-world system behavior. So let's get started. What are differential equations? A differential equation is an equation that relates a function to its derivatives. It describes how a quantity changes with time or with respect to another variable. Think of it this way: algebra gives you answer for numbers, geometry for shapes, but differential equations, they give you answer how things evolve over time. Differential equations that describe how something changes over time used to model real-world system. For examples are everywhere: mechanical systems like spring mass system, electrical systems such as circuits with capacitor and inductors, biological system, for examples, bacteria growth, environmental systems such as how pollutants spread. Whenever something changes continuously, there is differential equation behind it. Let's say we have a rule: the rate of change of variable y, function of time, depends on its current value plus an external input. This is a classic differential equation. It tells us not just where the system is now, but how it will move in the next instant. Why it matters? Differential equations are often called the language of change. In mechanics, they model springs, pendulums, and dampers. In electricity, they describe voltage and current in RLC circuits. In biology, they describe population growth and decay. In the environment, they show how heat or pollutants spread. Whenever you want to predict system behavior in the real world, you will need differential equations. First order linear differential equation. Let's move to the first main type, first order linear differential equation. The general form is here. Why focus on linear ones? Because they are easier to solve. A first order differential equation involves the first derivative of the unknown function y, t, y function of time, but no higher derivatives. General form here is here, linear. So we don't have a quadratic of y or more than that. So we have function of y here. Y is power of 1 only. Why focus on linear? Because they are easier to solve. They directly appear in the real problems like RC circuits, radioactive decay, and heat transfers. Linear versus non-linear. Let's see here. For example, we can see the linear differential equation here and non-linear one. Y appear with powers, products, or non-linear functions. But for for linear differential equations, we don't have any y square or sinus y. So why linear equation matters? Easier to solve analytically, directly used in modeling. For example, like in RC circuits, discharging capacitors, radioactive decay, heat transfers. Heat transfer here, for example, Newton's law of cooling. Separable differential equations, what is it? Separable differential equations is one you can cut apart, pull all the y terms and dy on the one side and all the t terms and dt on the other. Why it matters? Simple to solve. Because it's simple to solve, just integrate both sides. Work for many nonlinear equations. We have general form here. For example, we have dy divided by dt. We can separate the variables here. Y, dy and g function of y and function of time here with dt, and then we can integrate both sides. Example, separable differential equation. Solve, like for this example, solve the differential equation here. Step 1, separate the variables. Move terms involving y to the left and terms involving x to the right, and then integrate. Step 2, integrate both sides. We can easily compute the integrals. We can solve for y here, for y, and for constant c, it depends on the initial conditions. If we have x equals 0, what is the y here? It will give you the value of constant here. So the step 3, solve for y function of x. We can get y function of x here. And c is constant of integration. And for linear differential equation here, we can solve by these steps. Step 1, identify p function of time and q function of time from this general form. And step 2, find the integrating factor. So integrating factor is very important here. So it is exponential of integral of p respect to the time. Step 3, multiply the equation by integrating factor. This transforms the left-hand side into the differential equation like this, and we can integrate both sides, and then we can get the y function of time. Okay, and then for example here, simple example, determine the general solutions of this linear differential equation, first order linear differential equations. Let's identify the p function of time here, 3t squared. We can integrate it easily, and then we can get integrating factor, and then multiply both sides by integrating factor, and we can write the differential equations and then integrate both sides. We can get the solution of these differential equations. General solution of differential equations. So the constant c depend on the initial conditions or boundary conditions. And then let's move to second order linear differential equations. We have general form here. We have a1 and a0 is not 0. So a1 is not 0 and a0 is not 0 here. If f function of times is not 0, we call it homogeneous solutions. But let me repeat. If f function of time is 0, we have homogeneous solutions. But if we have f function of time here is not 0, then non-homogeneous solutions. This equation describes system with inertia like mass spring damper, RLC circuits. We solve them into step for general form. If we have f function of time here is 0, we have homogeneous solutions. The solution of this differential equation, we know y is, we can make guess here, y function of time is a exponential rt, and then let's differentiate the first differentiate y, and then second derivative we can get, and then let's put into the equation. We have this equation, quadratic equation. We get the equation. We can solve the r here. We can solve because it is simple quadratic equation, right? So the solution depend on the roots r1 and r2. If the root is real and distinct, we can write the general equations, the general solutions, I mean, C1 and C2 here, depend on the initial conditions. So this solution is for real and distinct. So R1 and R2 is different. And if R1 and R2 is equal, then real and repeated, we can rewrite like this. Or if it's complex, R1 and R2 is complex, then we have these solutions. And then let's move to the second order linear differential equation, non-homogeneous solutions. When f is not 0, we find particular solutions. We call particular solution YP, depend on time, common methods, undetermined coefficient, variation of parameters, final general solution here. We combine y for homogeneous solution and y for particular solutions. For example, we have this second order linear differential equation for non-homogeneous solutions. So we have f here is 4 times exponential minus t. We can get characteristic equations. And we can easily solve the quadratic equation here. R is minus 1 and R is minus 2. And then we can get homogeneous solutions because we have two distinct roots here. And particular solutions we can guess like this: a times t exponential minus t, and we can compute derivatives and substitute into the equation to solve for a, and we can find a for the final solutions. Let's more detail about the a here. So we have particular solution like this. If we differentiate first derivative and second derivative and then look into the differential equations, we can get like this, and we can substitute the first derivative and second derivative, right? And we can simplify inside bracket here, so we get a equal 4. So the particular solution is 4 times t exponential minus t. And the final step here, we can write the final solutions. So summary and takeaways content. We have learned differential equations, describe how systems change over time in physics, engineering, biology, and economics, and more. First, we have learned first-order differential equation can be solved using integrating factor method, often modeling growth, decay, and simple electrical circuits. And second-order differential equations are linked to oscillation, vibration, and mechanical electrical resonance with solution depending on root types. And non-homogeneous differential equation combine natural system response and external forcing. Practice is essential. Solving the real-world problems build understanding and intuitions. Thank you for your attention. Let's meet in another sessions. Thank you.